Welcome to JE Maths Unlocked, Problem of the Day. Today, we bring you a Korean CSAT style challenge. This elegant problem tests your deep understanding of geometry and limits, not just formulas, but true intuition. First, let's draw the diagram. Draw a semicircle, diameter AB equals 2, center O, so AO equals OB equals 1. Semicircle lies above the line segment AB. Mark point C on the semicircle. Angle AOC equals 90 degrees. Mark arcs and define points. On arc BC, place point P. On arc CA, place point Q. Choose P and Q such that PB equals QC. Place a point R on AP such that angle CQR equals 90 degrees. Let S be the intersection point of AP and CO. Angle PAB equals theta. Mark and shade relevant regions. Triangle POB. Quadrilateral CQRS, where f of theta equals area of triangle POB, g of theta equals area of quadrilateral CQRS. Let's now dive into the solution. We'll begin by carefully finding expressions for both functions, f of theta and g of theta. Once we have those, we'll substitute them into the limit expression and simplify. So, let's start with the first part, finding f of theta. In triangle POB, observe that chord PB subtends angle theta at the circumference point A, since angle PAB equals theta. By the circle angle theorem, the angle at the center is twice the angle at the circumference. Therefore, angle POB equals 2 theta. Now, to compute the area f of theta of triangle POB, we use the sine area formula. Plug in all the values. We get f of theta equals sine theta into cosine theta. Now, let's move on to finding g of theta, the area of quadrilateral CQRS. This part is going to be a bit more subtle, so let's break it down step by step. Start by focusing on triangle POB. Notice that angles OPB and angle OBP are both equal. In fact, each is 90 minus theta, because the angle at the center angle POB is 2 theta, and the triangle is isosceles with sides OP equals OB equals 1. Now here's a key observation. Triangle POB and triangle COQ are congruent. They have equal sides and equal angles by construction. That tells us that angle QCS is also 90 minus theta. Now shift your attention to triangle AOS. In this triangle, look at angle ASC. This is an exterior angle, and it must equal the sum of the opposite interior angles. That gives us angle ASC equals 90 plus theta. So now we have two angles, one at point QCS equals 90 minus theta, and another at ASC equals 90 plus theta. Together, they add up to 180 degree, which implies that lines AP and QC are parallel. And that's the breakthrough. This means quadrilateral CQRS is a trapezium, and as we know, the area of a trapezium is given by 1 by 2 into height into sum of parallel sides. We'll use that next to compute g of theta. G of theta equals 1 by 2 into QR into QC plus RS. We'll now find each of these values, starting with QC, then QR, and finally RS. First, consider segment QC. Recall that QC equals PB, by the given condition. And in triangle APB, angle APB is 90 degrees as this is made in semicircle now. Using the sine rule we find PB equals 2 sine theta. So, QC equals 2 sine theta. Next, to find QR and RS, we use a clever construction. Drop a perpendicular from point S onto line segment QC, let it meet at point T. Now focus on right triangle TCS. In this triangle, TC equals CS sine theta, TS equals CS cosine theta. To find these lengths, we need to determine CS. Observe that CS equals OC minus OS. We already know OC equals 1. To find OS, look at triangle AOS. From the right triangle AOS, we have OS equals OA tan theta. Therefore, CS equals 1 minus tan theta. Now substitute back the value of CS to calculate TC and TS. TC equals 1 minus tan theta into sine theta, which simplifies to sine theta minus sine theta tan theta, and TS equals 1 minus tan theta into cosine theta, which simplifies to cosine theta minus sine theta. From here, you'll be able to plug in values to compute QR and RS. Now, let's look more closely at the quadrilateral QTSR. Notice, it forms a rectangle. Why? Because we dropped a perpendicular from point S to QC, forming right angles at T, and both QR and TS are parallel and equal in length. So from this rectangle, we get QR equals TS equals cosine theta minus sine theta. Now, let's find RS. Since QTSR is a rectangle again, we know RS equals QT. And QT equals QC minus TC. We already found QC and TC. Substituting those in, RS equals 2 sine theta minus tan theta into sine theta, which simplifies to sine theta plus sine theta into tan theta. We now have QC, QR and RS. We're now ready to plug everything back into the trapezium area formula for g of theta. We get this, and that's our expression for g of theta. In the next step, we'll substitute both f of theta and g of theta into the limit. Let's move ahead and evaluate it. Now, we substitute our expressions for f of theta and g of theta into the limit. We get the limit expression as this. Now, let's simplify using the standard limit. Theta tends to 0 sine theta by theta equals to 1. Substituting and simplifying the expression step by step, the terms rearrange and the limit resolves beautifully to 2. And that's our final answer. Thanks for solving this elegant Korean CSAT style geometry and limit problem with us. For more such insightful problems, stay tuned to JEE Maths Unlocked.